Yes.
Cool. I'm so
I
glad.
do remember sets.
Well, because one no would have had the vote. Cool. Well, today, this is crooked. No, it's not. There we go. Today, we are once again doing sets, and we're still kind of like in between everything. And so I'm going to say right now, we are in section 6.1 / 6.2 / 6.3. Because once again, we're doing it out of order. And today, if everything goes well, we're going to be covering set operations, set identities, there we go, and the empty set, and maybe disjoint sets. We'll see what we get to today, Herman. It's me and you. So yeah, so let's just start by remembering what the hell set operations are again. And just like logical operations or arithmetic operations, I don't like this yellow light. There we go. Just like logical operations or arithmetic operations, set operations are just ways to combine one or more sets to make a new set. You could also only have one set, just kind of how you could do like not a statement, right? And you get like the opposite of the statement, but still also a logical operation. And so our logical operations that we care about, the four, like there's plenty more. The ones that we care about are the following. So let's go ahead and let you be the universal set. So we're gonna have you be the universal set. And all that means is that in the context of what we're talking about, we're gonna consider everything to be a subset of U. U is the universe we care about, whether it's numbers or matrices, or, I mean, if freaking, it could be anything. I like goats for some reason. I don't know why I like the example of goats, but it could be a set of goats. The point being, U is on the universal set, but this is not to mean that U is the set that like contains all sets or something like that. No. That's the whole reason we want to bring U up to begin with, because there is no like universal set that contains everything that we could possibly imagine. And we can talk about that for a second. There's some weird contradictions that come up if you start talking about that. But so there is no overall universal set. And so whenever we're working on a problem, we have to pick a universal set to be the context of our problem. But I'm just going to call it U. But if we're doing a real problem with real things, we would say U is the real numbers, U is the complex numbers, U is a set of matrices, or whatever the context is. But here, so U be the universal set, and let A and B be sets in this universe. Then we have four logic operations that we talked about last time. We have the union, which symbol is just like a U, basically, really nice and simple. In LaTeX, it's called a cup, interesting enough. We have the intersection. And the intersection has like the downward cup symbol, which LaTeX calls a calf. I kind of like that. We have the set difference. The set difference being, we could use the minus sign or the backslash sign. And then we have the set complement. And the set complement uses a little superscript C. So, well, wait a second. Interesting. There you go. So, the point is, the union is a union of two sets. So we do the union of A and B. And what we said that equals is this equals all x, the universal set, 'cause that's the context we care about, such that x is in A or x is in B. So it's just like remember we had two statements, right? An or statement kind of brought in what you were talking about. Like if you like spaghetti or meatballs, well, actually, wait. Let's not think about that. Anyway, the point is that if x is in use, x is in A or x is in B, that means this set contains everything in A or B. So it's A, it's both of these sets kind of put together. So it makes it larger. Whereas the intersection is A intersect B, which by definition, this equals all x, the universal set that we care about, such that x is in A and x is in B. The important thing being there that if you're in A and you're in B, A intersect B, this is making the set smaller, kind of. Because it's not just everything in A, or everything in B, they have to be in both. So it's that intersection, the middle of the Venn diagram. Whereas this is everything. So that's kind of interesting. And then we have A minus B. And this is the set difference. And so this is kind of like exactly what we want it to be. This is just everything in A, but get rid of all those B's. And so this is going to be everything in U such that x is in A and x is not in B.
For subtraction, does the order matter?
Very much so. Yeah. So good question. So for example, if we did, for a real simple example, 1, 2, 5, 7 minus 3, 4, 2, 5. Right? This would be, you go through and you go, okay, it's going to be 1, 2, 5, 7. But I want to get rid of everything that shows up here. So 3s, no 3s, so you don't have to worry about it. 4s, no 4s, don't have to worry about it. 2 shows up. And 5 shows up. So I want to take this step and get rid of everything that's in this set. And so this leaves us with 1, 7. Whereas we did the opposite way around, 3, 4, 2, 5 minus 1, 2, 5, 7 like that. Now we go through, we go, okay, let's look at 1, that's not here. 2, oh, that shows up. 5, that shows up. 7, doesn't show up. And so we have 3, 4. And so what this really captures is the difference captures the amount of this set that pokes out of this set. Or the other way around, the amount of this set that pokes out of this set. And so if we were to draw our Venn diagrams, right, if we had like A and B and we're in U, not U, but U, and then we had A and B like this, so blue is always B, red's always A, damn consistent. And now let's look at A minus B here. This is everything in A that pokes out of B, is the way to think about it. So that's just going to be all of this stuff right here. But then B minus A, that's everything in B that pokes out of A. And so that's going to be all this stuff right here. And so we kind of get opposite things. If that makes sense.
Yeah, that makes sense.
Good, nice. But actually from here, let's just notice this for later maybe. Notice it looks like, check it out. If you're in A union B, that means you're in one of the balls or both, right? One of those sets are both. It looks like you're either going to be in A minus B, or you're going to be in B minus A, or you're going to be where? So this side's A minus B, right? This side's B minus A. What part did we not reach with these two of A union B of everything of these two sets put together?
Is it A and B?
Exactly, A intersection B.
Sweet. Okay.
Yeah. We didn't reach this little part right here. But if you put them all together, we actually get everything. And this is going to come up later. I will say, recall this for disjoint sets when we get there. Anyway, though, we're not there yet. So let's stop recalling and start learning. I'll tell you when it's time to recall. I say it's time to recall in this class. Yeah, these are our 4-step operations. And then I started talking about this last time, and that is that the very first thing we did in this class was basically talk about logical operations. But we talked about what a statement was. Once we had what a statement was, we talked about logical operations, way to combine statements. And then once we had what logical operations were, we talked about logical identities, right? Like ways that some statements were the same. And so we had, for example, De Morgan's law, which says that not P and Q is logically equivalent to not P or not Q, or we had everything like that. But that was interesting because, these logical operations were ways to combine two statements. But we started to notice that a lot of these ways to combine two statements that are complicated enough, they started to overlap. There were some ways that were equivalent to other ways. And so these set identities gave us nice ways to prove things, everything like that. And same thing here, right? We have, once we define what sets were, like 3 classes ago, we can now talk about set operations. Once we have set operations, we can talk about set identities, because some of these operations are put together in the right way, we can maybe already start to see are gonna kind of relate to each other. So, but before we do that, let's just do a complicated example of, like using a bunch of wait, sorry, I didn't want to have a complement. Oh, that right now real quick, my bad. Complement's easy. A complement, this just equals, or sometimes we say not A, this just equals all X in U such that X is not in A. That's why we call it not A. There's everything not in A. Sorry about that, Herman.